Welcome to our Introduction Networks ITC class meeting for the week of 10/17/17. I appreciate everybody being here, and I appreciate you dealing with the day change this week. I apologize. I've got to travel tomorrow, so needed to make today our class meeting. Today we're going to talk about the network access layer, which when you think about what we discussed last week and we talked about different protocol models, we talked about the OSI model and we talked about the TCPIP model. And we talked about the 4 layers of the TCPIP model and the application, transport, internet layer, and network access layer. And when we talked about looking at how those layers of the TCPIP model relate to the OSI model, we talked about how the application layer, the presentation layer, excuse me, can't type today, and the session layer, how all of those map to, in the TCPIP model, the application layer, because the functions are performed at the application layer of the TCPIP model. We talked about the transport layer of the OSI model and how that directly maps to the transport layer of the TCPIP model. We talked about the internet or the network layer and how that maps to the internet layer. And then last, we had the data link and we had the physical layer. And those two map to what the TCPIP model called the network access layer. Okay. And that's where the title of this particular chapter comes from. We're going to be talking about the physical and data link layers of the OSI model. So we're going to be talking about cabling and those specifications that deal with encoding and items at layer 1 of the OSI model. And then data link, which deals with framing, encapsulation, and anything to do with framing of information onto the media or medium. We are looking first in this chapter at the physical layer. We're going to look at different types of connectors, different types of ways to connect to your particular Cisco devices or devices at all. Everything from straight through cables to crossover cables to different types of cabling. When we look at layer 1, the big thing at layer 1 is, remember, it is a bit pusher. Layer 1 is dealing with just how do you get signals on the wire. Is it a 1 or a 0 based upon an electrical signal and the electrical signal measured over time? Is it a 1 or a 0 based upon the presence or absence of light? Each one of those are a different way of encoding binary information onto network media. We talk a great deal about layer 2, which is the data link layer. And when we talk about that, we talk about the Ethernet NIC, or we talk about NICs, because they're going to be the items that have our media access control and our physical addressing on them. The physical layer is down here at the very bottom. It is just 1s and 0s. It is the bits pusher of the networking world. I call it the blue-collar worker of the networking world, because all it does is make things into 1s and 0s. And it's based upon what type of cabling you're using as to how it becomes a 1 or a 0. You remember that the source node encapsulates the information down through the 7 layers, or if we're discussing this in terms of TCPIP, the 4 layers, down the physical layer, sends it across the media or medium, and then on the receiving end, the destination node is going to de-encapsulate it. I think it's very interesting to note here that you're going to have data link address and information, and this address and information at the data link layer is what's called physical addresses, because it's burned into the network interface cards, but if we're using Ethernet. At the network layer, you're going to have information that is a set of logical addresses, and we'll talk about the difference between a logical and a physical topology as we move throughout this chapter. So physical layer media has many different types of signals that can be used. On copper, it can be electric signals, or it is electric signals. So it's the presence or absence of a certain current or voltage over a time slot. It's always over a particular time slot. Same thing is for fiber optic cable. You've got the presence or absence of light. And then under wireless, you've got different types of amplitude, frequency, so AM, FM, pulse modulated, different types of encoding methods. Now, you don't have to remember all these encoding methods, But it is important to kind of know that these standards are set by different groups out there. And for the layer 1 standards and some of the layer 2 standards, so some data link standards too, the ISO, EIA, TIA, ITU, ANSI, and IEEE are all responsible for setting some of these standards. That's why we see a cabling standard that is EIA, TIA 568A and EIA, TIA 568B, so that we have multiple standards that can be used, but they are set at the physical layer. Now there's a lab here. In this lab we really cannot do in NetLabs, so this is something you'll need to do in your classes and also yourself, and that is just go into your lab and look at the different pieces of Cisco gear that's there and look at the different types of ports, look at the different media in your particular classroom. For me, I've got unshielded twisted pair cables that are both crossovers and straight throughs. We'll talk a little bit about what those are in a minute. But I don't have any coaxial cable at all. I'll just tell people to go look at their cable connection at home. But we do have a lab on that for you to use inside of the class itself. So when we look at encoding, here's an example of Manchester encoding, which is the absence of a voltage is a particular state, either 1 or 0. The presence is another. So you see the transition occurs in the middle of the bit period. So in this case, there's a time slot, and whatever is represented or whatever is found at that time slot will be what you can determine as a 1 or a 0. We look here, it can be a you can look at modulating wave or FM. This obviously is a binary signal here, but you can use the presence or absence of voltage to figure that out. Manchester encoding is one of the most common types of encoding. And it's just looking at how you represent a 0 or a 1. So high voltage can be a 0 or a 1, or the transition from one to the other can be also known as a 0 or 1. So if it stays at a certain level and doesn't change its voltage in the time slot, then it doesn't change state. Here's an example of it actually changing. So it's translating itself through this time slot. Other different types of signaling, of course, is free FM, which we are familiar with, FM radio, and AM radio signals. You can see the different signals, and you're looking at amplitude, frequency, how many wavelengths you have in a certain time slot, and you can end up with a modulating wave, a carrier signal, and you get an FM signal. Now, I'll be the first to tell you, I don't understand every single thing about FM and AM modulation or Manchester encoding. I just understand the basics of how that particular process takes place. Now, when we look at bandwidth and throughput, I always give people an example like this. Let's think about bandwidth. Bandwidth is the maximum capacity of a media or medium. So bandwidth is your maximum capacity. A great way to think about bandwidth is, do any of you have a hose pipe or a garden hose?
Yes.
Yes. All right. So you've got a garden hose. You can turn the water on full, all the way on. And if you fill the entire garden hose up and water's coming out as fast as it can, you're using all of the bandwidth. So your throughput, and that's the difference. The throughput is the amount of information flowing through a medium. And I'm just going to put data for us, it's easier. Flowing through a media or medium. So if you've got the hose pipe or the garden hose wide open, your throughput and your bandwidth are the same. But you don't always do that, okay? You don't always have your garden hose wide open. So throughput is how much is actually going through your media or medium. I can't spell today. All right. So if you've got a fire hose, the fire hose has this huge bandwidth. Throughput is how much water is going through that fire hose at one time. We also have a concept they don't even talk about in the class really, but goodput, and this is the amount of data minus control information that's flowing. that's actually flowing. So not everything that goes through your media or medium is actually data. Some of it is control, retransmission, clocking information, those types of things. So the bandwidth, again, remember, is the maximum you can get on a piece of media or medium. Now, what's the maximum we can do on unshielded twisted pair cabling right now? They're working on 100 gigabit Ethernet. They're actually working on even faster than that on copper cable. On fiber optic cable, really the maximum amount of information that we've been able to put on it is limited by what we can put on each end. So we're still trying to find out what the maximum would be for fiber. The good news is as we continue to use fiber more and more, we will develop faster and faster technologies. Another good thing is it used to be in our older technologies when we were using Ethernet at the data link layer, and Ethernet was a truly contention-based technology because of collisions. Your good put and throughput will not, you would have a great discrepancy because you have a large number of retransmissions. In today's networking world, we don't have that as much because we have fully micro-segmented networks where switch ports are handling the switching of information without collisions taking place. So here are a couple different bandwidth rates that you can look at, and it is bits per second. That's the fundamental unit. Kilobits per second, 1,000 bits per second, megabits per second, gigabits per second, and tetrabits per second. And there's terabits per second, not tetra, terabits per second. And then there are even faster speeds. What's going to determine our bandwidth? The properties of the physical media and the technology you're hooking onto each side of that physical media. And again, throughput, the amount of traffic going through your media or medium. So bandwidth and throughput do not normally match exactly. Okay, and they do actually mention good put in here. Okay, good. Forgot they had done that. But good put is the usable data being transferred versus control traffic. So what are our different types of media we're going to talk about? On a typical 1941 router, as you see here, you've got Ethernet ports which use unshielded twisted pair. This is a synchronous synchronous, can't remember what the H stands for, but synchronous DSL. I know what DSL stands for, which would be more like a RJ11 connector that goes in there. You can use an RJ, I believe I use RJ45 also. Management ports which require an RJ45 or a micro USB, and of course our Ethernet ports that use our typical RJ45 connectors, and we'll show some pictures of those. Now, copper cabling. Why do we like copper cabling? Well, one reason is it's cheap. Even though if you go try to buy a copper cable that's pre-made, at certain places it can be very expensive, but for the most part, copper cables are cheap. They have a fairly good distance run limitation. Does anybody know what the distance run limitation is for unshielded twisted pair cabling?
100 meters.
It's 100 meters. Yep, 100 meters or 328 feet. And the way that is normally broken down, it actually, believe it or not, there are actually specifications, which is 6 meters from the wall to PC, 90 meters from wall to punch down, and then 3 meter patch in closet. So, and I know that's only 99 meters, but that's what it is. Okay, they give you a meter to fudge. What's the problem with going past 100 meters?
Attenuation.
Attenuation, which is one of our main topics with any type of cabling. Attenuation, which is the loss of signal strength. Yeah, as a signal travels through a media or medium. Why don't we use copper? Why don't we use copper for our cabling?
Why?
Yes.
Cheap.
It's cheap.
Flexible.
Also great, flexible, very flexible. Great conductor.
Good electrical conductor.
Exactly, great conductor. Okay, so it's one of the reasons we use it. So it's cheap. It's a great conductor. The signal can go a decent amount of distance. The other item I want to talk just a little bit about, I'm going to put this on here so we can kind of put it on, but crosstalk is another item, and that's signal overflow from adjacent wires. and we'll talk about that with unshielded twisted paired cabling. Here's an example of a pure digital signal. Here's an interference signal, and then when those two come together, you get a change signal. In other words, what should have been a 0 is a 1 now because of the registered voltage. The amazing thing here is the further you go along a cable or any medium, your signal strength degrades. Now, there's ways to fix that. One is you can put a repeater in there, which is something that can be done depending on how far you've got to travel with the information. That's what they had to do in my DSL link. They came in and put a repeater in so we could go to a faster speed. The same thing can be done with fiber optic cable. You can put in an amplifier to amplify the signal and send it on. But there are issues with copper cable. One is, of course, attenuation. It's only able to go 100 meters. It is extremely conductive, so you don't want to use copper cable between buildings. Anywhere electricity could be an issue, or there's a chance of a change in electrical potential. So between floors in a high-rise building, you have to be very careful because you can actually have the information or have electrons move towards that change. Okay, and so we have to be careful of that. Also, another item is electromagnetic interference. If you have motors or if you have anything that causes EMI, you have to be very careful with copper cable because it can interfere with the cable. Having said all that, it's still the most common type of cable that we use. We use unshielded twisted pair cabling, and we've moved into using some shielded twisted pair cabling depending upon the speeds that you're using. And then the other item and the other types of copper media we use is coaxial cable, which has been around since the beginning of the dinosaurs. One thing I want you to notice here, this is a good way to see it in this picture. On the unshielded twisted pair cabling and on the shielded twisted pair, look at the rate of twist of the wire pairs. You'll see that the white blue blue is very tight. The white brown brown is not that tight. White green green, white orange orange. You'll notice they've got a different rate of twist. This is to help prevent crosstalk. This is to help with the idea that the signals that overflow will be out of sync with one another and won't cause problems across the wire pairs. Likewise, you'll see the shielded twisted pair. This shield right here is designed to help with EMI interference. And then you've also got this plastic in the middle, which helps to keep the wires in the correct place. And does a little bit for interference, but not much with crosstalk. That's more to give it stability when you put it into the connector.
We used it for crosstalk, or to limit crosstalk, or minimize it more in secure facilities.
And it is. I mean, and the other thing is, it helps to minimize crosstalk between two shielded twisted pair cables beside each other.
Right.
You know,
and that's
not so much.
basically
Yeah.
what we were using it for.
Yeah, and that's a very common use too. So it can be used for either way. Either letting the bad news about unshielded twisted pair, you can actually lay it into a device and you can actually pull all the electrical signals off of it and recreate what's going across that cable. With shielded twisted pair, it's much more difficult to do that because the shielding is designed to keep the signals from leaving the cable or having anything come into the cable, one or the other. I will say this, so if you really need security, you need to be using fiber optic cable. There's really no other cabling.
Yeah, this is about 20 years ago when that was really not financially feasible. Yeah,
it wasn't at all. And it is amazing now how much cheaper fiber optic cable is. It's really almost, the last time I looked on a per foot basis, it's not that much difference. The big difference is just getting it terminated.
The hardware.
Yep, the hardware and the termination is what costs you all the money now, which is amazing. And then this coaxial, it actually is more resistant to EMI than UTP or STP because it's got two sets of shielding. It's got the copper and it's got a copper shield and an additional copper shield around it. So it's a little more resistant. Here we have the outer jacket, obviously protects from copper. Now, one thing I will mention to you, if you've never heard of it before, there's a thing called plenum. Anybody know what the plenum is?
Yeah, it reduces the amount of toxic emissions in a fire.
Exactly. So if you're running cable, unshielded twisted pair cabling through the walls and ceilings, in many places the fire code requires you to use a special type of cable that is not made of PVC. It's got a different type of, well, it's made of PVC, but it's more resistant to fire, and it also is made where it will not give off as toxic a fumes as normal burning plastic will. So plenum-rated cabling is something to keep in mind if you're running cables through walls or through ceilings. Still twisted pair, protects interference, and you got color-coded plastic so you know the wire pairs. You'll hear I say white, orange, orange. You'll hear a lot of telecom people say orange, white, orange. It's just the way telecom people do it sometimes. The jacket, outside jacket on twisted pair is a little bit thicker than on unshielded. You've got your fall shield. You can even have fall shields around each individual pairs, and then you still have 4 pairs or 8 wires. Harder to work with, harder to terminate, but more secure. Coaxial cable has a center copper conductor that can be either stranded or solid, depending on which one you use. It's got a plastic insulation, braided copper shielding, and then you've got the outer jacket. And there's a couple different types of connectors here. BNC, which is either bayonet or British naval connector, depending on whether or not you're British and you think you made it. The N-type is a type, honestly, I've never used, but I have used the F-type because this is what we use with our RG6 cable that is for cable vision, cable, that type of thing, or satellite TV. I've got like 1,500 feet of satellite RJ6 in my house. So when I built the house, I figured I've got 3,500 feet of Cat 5e and 1,500 feet of RG6. The joke is a tornado couldn't pull my house apart because of all the cabling on it. Some safety items with copper. First, again, make sure you are using the correct rated cabling for where you're installing it. You also need to make sure you're up to date with the fire codes and with the installation codes for your area. Your area can be very different from mine. In other words, low voltage cabling installation requirements. Some places require a license, some people don't. Like when I built my house, I could put in all the Ethernet, all the RG6 I wanted to. I did not have to have any type of electrician's license, nothing. But that's the code for where I live. Each one of your students and where you live needs to look at the codes in their area, and it may be different from county to county. So that's very important. Cables need to be connected correctly. You need to be very careful as far as grounding, especially if you have a difference in potential, because this is copper cable, and you can end up with a situation where your charges are moving between different levels of a building or within different sections of a campus. So that needs to be very careful. Quite honestly, if you're going between buildings or between floors in a building, it's just best to use fiber optic cable. Any questions about that, about basics of copper cable?
I'm good.
All right. Again, cancellation using wire pairs, using twists. Here's a couple different categories, and this is just some of them. Cat 3, which is rated for up to 10 megabits per second. Cat 5, 5E, which will go up to 100 megabits and 1,000 megabits. It will actually do 1,000 megabits, Cat 5E especially. Cat 5 will not, it will do it, but it's not recommended. And then Cat 6 is designed to go up to 10 gigabits, although 10 gigabits is not recommended. When we start getting into 10 gigabits, we're looking at using fiber. We're also looking at using possibly twin-ax cables or some type of other special cable that is just for short runs in our data centers. There is a Cat 7, which they don't mention here, which is also ready to go even faster. And as we move forward, I really think we'll see more and more as we go forward. And you notice Cat 6 has got these shielded foils around each pair to keep them from interfering with one another.
Question for you.
Shoot.
I was talking about Cat 5e, or actually Cat 5 going up to, what is it, 1,000 megs per second?
Yep.
But it's not recommended?
No, that was just Cat 5, excuse me, that was, yeah, Cat 5. Cat 5e will do it. Cat 5e will do 1,000. Yeah,
but it says Cat 5, it's not recommended?
Correct.
What damage is it going to do?
Well, here's the problem, and it will work, but the problem becomes this: if you don't terminate the connectors exactly correctly, if you don't do it perfectly, if you happen to exceed the the 100 meters by just 1 meter, or as you approach that 100 meters, any problems with connectors in the distance. So really what happens with Cat5, there's not a lot of wiggle room for it to not, basically for it to not have errors at 1,000 megabits per second.
So
if you do everything right, it will support it.
Well, I guess my question is, I think it not recommended as it would damage something.
No, no.
It's not really capable of it, so why advertise it at that speed?
Right. It won't damage anything, and it will run. I mean, what happens is, in most cases, you know, if you're going to put in cable today, you're going to put in Cat6, Cat7, depending on what. The problem with Cat6 is, I was talking with a guy today who had to do some installs. It's just a pain to put ends on Cat6 cables.
Yeah, the
and
terminations.
So, the termination is so much harder. But if I was going to go back and put my house in today, you know, put it in today, I would do Cat6, you know, no doubt. The difference is you hit some buildings that already have Cat5 installed. And so what I think they're wanting to say here is that just because it's Cat5 doesn't mean you can't do 1,000 megabits per second, you know, do gigabit Ethernet, but be aware not every link in that will support it.
Right.
So, and so that's why I think they're saying that. Yeah, loss of performance. Yeah, I think that's true. Keisha's talking about no false hope in performance. Yeah.
Yeah,
so,
and that's what I would assume that would happen. I mean, you know, some of these installations, they may tell you it's 100 megs per second, but you'd be lucky to get 50 out of it.
Exactly. Exactly. Well, and you know, the problem there becomes, especially let's say I go and I'm going to put in new gear in a building. I test it, and most of the links it's all Cat5 cable. Am I going to put the money in to pull a new Cat5e cable, or am I going to take my chances that 80% of my links will run at a gigabit and 20% will run at, you know, fast Ethernet?
I guess my thing is most users aren't even really going to notice that they're running at 50 megs per second versus
right
gigabit.
Right.
Unless you're sending unless it's a really data intensive program that they're running.
Right. And as long as there are not errors on that link, you know, if you're getting errors, that's a whole different ballgame.
Yeah.
Agreed. I do agree with you on that. I do think one of the things that's going to be very interesting, have any of you read about the new 5G standards that are coming out?
No, I was going to try and look those up.
I haven't done a great deal of looking at it, but those 5G standards look very interesting because they're talking about the problem with them right now is the 5G requires direct line of sight, so they haven't solved some of those issues with it, but the speeds are just phenomenal. So they're actually looking at this could be the beginning of replacing wired internet connections to your homes, which, like I said, I get much faster connections through my phone at my house than I do with my regular wired cable, you know, or DSL. I got DSL. So it's kind of funny. I can do a speed test with my wireless off, and my phone's much faster than it is otherwise. So it's
and that's direct line of sight.
Yeah, that's what they're saying with 5G right now. It's direct line of sight, but they're going to figure out ways to bounce it off buildings, bounce it off other things. So it's going to be interesting to see what they end up doing with it.
Yeah, because there'd be a lot of extra towers around.
Yeah, you're not kidding. And they're not fooling anybody. Those things really aren't trees.
No.
that kills me when you're driving down the road and you're like, why bother? You can tell it's a tower, but
yeah,
pretty funny. Here's a couple of our. Go ahead, Kira. Okay. Here's a couple of our RJ45 plugs. You can see there are 8 wires, 4 pairs. Here's a modular UTP socket or plug made by all different types of vendors. One of the things I will remind you is there are 2 standards, 568A and 568B. I've used mostly 568B, and when you do, make sure you buy your connectors and your patch panels to be the correct type that you're wanting to use. If you want to run all 568B standard, buy 568B patch panels, and make sure you use 568B wiring on your connectors, on your punch down items. Here's what not to do. On the left, that is a very bad connector. Couple reasons. One, the wires are untwisted. They're not covered by the sheath. The sheath is not up into the connector, providing support to the cable. Okay. You've been amazed. I always have my students make cables. That's one of the items in this particular section. It's not something that's easy for us to do in this class because it is online, but I do want you to make some cables in your lab. But this is how I usually get the first couple from people, and they're like, what's wrong with it? Because it's not going to give you the performance you want. And then after a couple times, we end up with them making decent connectors. It's also one of the things we usually do in our contests for Skills USA is we have them make cables and then use those cables. Even though I know most people buy cables today, it's still a really, really good skill to have. You'll notice here are the two standards, 568A and B. The only difference between them, pairs 1 and 2 and 3 and 6 are the primary pairs for send and receive. You will see that the difference is the white, green, green, and the white, orange, orange. 568A is white, green, green, white, orange, blue, orange, white, brown, brown. 568B is reverse of that, white, orange, white, green, blue, green, white, brown, brown. I memorized 568B, and then just know that I have to reverse the oranges and the greens to get 568A. If you want a straight through cable, you will pin out the pairs the same on both sides. Notice, and this is something I want to show you, I'll kind of turn on my, see if I can find it. Oh, yeah, I got one. All right, so here, obviously, is a connector. Just make sure when you're making the cable, you take it and you put the tab away from you when you're putting the wires in. So in other words, notice that it's tab away, and so pin 1 right on the very end here would be white, green, green, white, brown, brown, white, brown, white, white, orange, blue, orange, white, brown, brown. So when you make the cable, put them together and you turn the tab away and slide it in. If you do the same standard on both sides, you get a straight through cable. So in other words, 1 and 2 goes to 1 and 2 on the opposite side, 3 and 6 go to 3 and 6. If you want a crossover cable, put one tab away and then use the same standard on the other side and put the tab towards you. Oh, excuse me, that's a rollover. So that's a rollover. If you want a crossover, you do one side 568A and one 568B. It doesn't matter which side switch, just make sure you do one in one standard, one in the other. And that that crosses 1 and 2 to 3 and 6, and 3 and 6 to 1 and 2. So, used to be we had to worry a great deal about this because anytime you connected like devices, computer to computer, switch to switch, router to router, you would need a crossover cable. You don't need that anymore because almost everything this day and age auto crosses. It's auto MDIX, auto MDIX. So we don't have to worry about that as much, but I still teach it because you're going to get out there and find that 2950 switch that doesn't auto cross, and you're going to try to connect it to another 2950 switch, and you're going to end up not knowing why it's working because you don't realize you need a crossover cable instead of a straight through. Now, let me ask you this. If you're connecting a router's port to a switch, what kind of cable do you use? Okay, Keith said straight through. Y'all agree?
Say that again.
A router port to a switch.
Straight through?
Straight through. Okay. Good. Keith and Corey, definitely. Because here's why. The NIC on a router is considered to be, or the router's port is considered to be a network interface card. So if you connect a PC to a switch, you use a straight through. Same thing with a router to a switch. This rollover cable where you put the pin, do 568A, put the pin away, or tab away, and then roll it and put the tab towards you with the same 568A on the opposite side. That is how you create a Cisco console cable if you're using their proprietary console cable, which are Carolina blue in the box, and which are not in the box anymore. So if you actually order a router or a switch, you now have to order your console cables separately because they don't send you one. So, a couple things looking at with UTP testers, and there's all different types of, this looks like a tone tester here, but a wire map, cable length, signal loss, and crosstalk. And they make testers that do everything. And they will actually make testers that will print out a certification saying that this particular cable is 568A or Cat5e guaranteed or qualified. It's pretty neat because you get to do a white, green, green, white, orange, blue. Oops, wrong one. White, blue, orange. Oops, messed up. White, blue, orange. White, brown, brown. Now notice one thing I always teach my students is notice if you've done it right, regardless of the standard, there's no two solid colors beside each other and no striped colors beside each other. So that one is correct for that. And then you can go, and this tells you to do 568B. The only difference there is the difference is the white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. Now, this is no substitute for your student making cables because the manual dexterity to make a cable, trust me, after being hit by a truck, it's much harder with my hands than it has been before. So you do have a lab to do this, to build a crossover cable in the class. So I would like for you to build one of those in your lab at work. Do each of you have cable testing equipment and cable gear you can use?
Yes. Yeah.
Okay.
I used to have the students build them.
Oh yeah, yeah. Have them build them, and like I said, sometimes I always give them one example, and then it's it's amazing the number of cable ends that can be used in a semester. Keisha, yeah, you can do that. Just upload a picture of the cable if you make one, and if you're comfortable making cables, I'm not going to ask you to make. I made so many. You just if you're comfortable with it, I'm fine. It's just one of those skills I don't think we teach students enough of right now. Just for the ease of use of pulling your own cable and sticking it in the wall. So how do we use fiber optic cable? Well, fiber is used in enterprise networks between buildings. It's used fiber to the home. It's getting there. I don't have it. I don't know many people that do, but there are some that are getting it in metropolitan areas. Long haul networks, and of course submarine cables. I think it was Facebook, Microsoft just put in a cable across the North Atlantic, and they were talking about that and how it was one of the few times that two companies have worked together to put a big fiber in that was a cross-Atlantic cable. Here is what fiber looks like. You've got a glass core. Used to be there were some cores that were made out of plastic, but now everything's glass. You've got a cladding on the outside, which is slightly different from the core. And what it tries to do with the cladding is keep the signal in the core. And the core is usually no more than about the width of a human hair or less. Outside of that, you've got a buffer material, which helps shield the cladding and the core from damage. A strengthening material, which is typically Kevlar to help. And then an outer jacket that depends on what type of cable, whether it's an interior, underground, or other type of cable. The jacket will change based upon that. Single mode fiber is a type of fiber that has a single path for light, usually uses a 9-micron glass core, 125 micron cladding, and a polymeric coating. It's a small core. It is has less dispersion because it's designed for a single light path, and it's usually used for single mode over long haul distances. So 5 to 10 kilometers or more is what is used for single mode. Multi-mode is for shorter runs, and it is has a larger core, 50 to 62.5 microns. It has a coating on the outside and a glass cladding, just like single mode, but it allows for multiple paths of light. One huge difference between multi-mode and single mode is single mode usually has lasers as a light source, whereas multi-mode can use LEDs. Regardless, one of the things I always teach students and instructors is never, ever, ever look into a piece of fiber, no matter if you think it's not connected to something other end or not, because it can immediately blind you. So only look, if you're using fiber, only use a fiber tester to check it. Don't even shine it on your hand because some single mode lasers could actually burn your hand. Different types of connectors. Here's how I teach people these. ST, I call them simple twist, because STs you push on and twist them to lock them. So STs are simple twist connectors. SCs are simple click connectors, so you click them in. LCs, and they're all dual LCs, multi-mode LCs, those are also clicks too. So each one of these clicks in, and then this is a twist. Most everything's gone to the SC that I've seen recently. And tell me if I'm wrong, everyone. And they call them straight tip versus the SC, but the bayonet, I call them simple twists because they're easier. Here's a couple fiber patch cords, pretty common. Here's an example of an ST to an LC. He's got some older gear that uses one to the other. So single mode is yellow, and multi-mode patch cables are orange. So that way you can know them apart. Some of the things with an OTDR, optical time domain reflectometer, this is a fiber testing device. You could have misalignment of fibers that have been spliced. You can have gaps where you did not completely get the end connector on, or you haven't plugged it all the way in, or the end finish, there could be dirt on it. That's why when you actually put an end on, you actually take the fiber and you buff it and get it clean. Fiber versus copper, big difference is copper is cheaper, okay? It is not immune to EMI. It is cheap. It's easy to install. So copper has its advantages. Fiber, however, has very high bandwidth distance support. It has extremely long distance support. It is completely immune to EMI and any type of electrical hazards, but it also is the most expensive in terms of media and connector costs and installation skills. Safety precautions, I don't really agree with this. You know, fiber optic cable is really no more dangerous than UTP. I mean, you can poke yourself with the fiber or whatever. You don't wear glasses like you should. You can get it in your eyes, but you can do that with UTP too. So I don't particularly buy that one. I'm just going to real quickly blow through wireless. Pretty much everything is going wireless. We know this. We know that new standards are coming up all the time. 802.11 standards continue to evolve to get faster. We've got MIMO devices, multiple inputs, multiple outputs, which gives us multiple antennas to allow for even more speed. You know, you have a wireless access point and a wireless NIC. I'll give you a very interesting wireless anecdote. I have a Surface Pro workstation, Surface Book Pro with the performance base, super fast laptop, awesome laptop, love it. But at home, I would do a speed test and get like 1.2 to 2 megabits per second. And it only started doing this after I replaced my home router. I put a different router in. Before that, it was fast, no problem. Did some research, kept doing some research, found out that Surface Book Pros with only certain types of access points have a problem, and you have to go in and make one change to the registry, and that change will fix the issue. So I made change a 1 to a 0 in the registry, and it had to do with the way it handled layer 2 framing. And second I did that, I'm at 11 megabits on my Surface Book Pro. So there are weird little things like that with wireless that you won't see on a wired connection. It's one of the reasons why I have wired connections everywhere in my house that I can. If I can wire it, I wire it. But you'll see most of the people today would just soon have everything wireless as wired. Okay, questions about the physical layer? Nope.
I'm good.
All right, well, let's talk about data link layer. Now, the data link layer deals with framing. It sits between the pure physical media, and this is where, folks, we talk about the transition from physical to logical, because you can pick up a piece of UTP, you can pick up an RJ45 connector. You can't really pick up a MAC address. Now, you pick up a chip that has it burned into it. But then once you get up to layer 3 is logical addressing. Layer 3 does not have any physicality, really. You can't touch an IP address. So the data link layer is that boundary layer between the upper layer software components and the lower layer hardware components. It's for that reason that the data link layer is going to be broken into 2 sublayers. We'll talk about those. Those are the logical link control sublayer, or LLC, and the MAC. And I tell people to remember this by just saying MAC LLC, like it's a rap group. So the MAC sublayer deals with media access control. In other words, the process of putting frames onto a media. We talked a little bit about it last class. We talked about contention-based methods, and we talked about contentionless methods. So we talked about ring or token rings or token passing as a contentionless method. And we talked about Ethernet's method of CSMA, CA, and CD, which we'll talk more about in a second. But how do you put information on to the wire itself? How do you frame it? MAC layer also deals with the MAC addresses, which are the physical addresses. LLC is a logical link layer that serves as that intermediary between these lower layer physical components and the upper layer logical components, so the IP addressing. So LLC is how you pass things up to IPv4 and IPv6. And that's how you can allow multiple layer 3 protocols, because you can just rewrite the LLC sublayer instead of having to completely rewrite the entire data link layer. So be aware of that. That's very important to know. So here's one really neat thing too. As information travels from one device to another, layer 2 is changed at every single hop. And in this case, you can see it was first Ethernet, then it became light, then it became a radio wave, then it came light again, then come down, and now it's wireless over here. So at each hop, okay, the data link protocol can be different and it can change. The purpose of the data link layer is to provide access to media. In this case, you see a LAN header, which would be the MAC addresses. It goes up, it gets a WAN header, so whatever this happens to be, which on Cisco routers, by the way, it's HDLC is the default on serial connections. And it goes across. So the data link layer is going to take the information and encapsulate it into a frame, send it down to the physical layer, it gets encoded into whatever method of encoding is needed for the media. Will go across, and the opposite side will de-encapsulate it. Same groups that do the standards for the physical layer, many of them do the standards for the data link layer. And now let's talk about how we control access to the media. I've talked a little bit about this. One is, how do I share this particular media? In the old days, this is actually how Ethernet looked. We had a bus, and in each one of these buses was connected to an RJ58, or excuse me, each one of these machines were connected to RJ58 via T connector, BNC T connector. And you would literally have to, this machine would listen, all right? Remember I talked about an access method called CSMA CD. So each one of these machines would have to perform a carrier sense and listen to see if the wire was in use. If it was not, it would then send. And because every machine could listen at the same time, multiple access, it was possible for 2 frames to go out at the same time and collide. The first machine to see that would send a jam signal and say there's been a collision. And everyone performs what is known as the back-off algorithm. And that would then force them to retransmit at a random time. We no longer have physical buses. We have physical stars. Okay, so here's really what looks more like a star. And then the logic is different. So we may have a logical network here, even though physically it looks like all of this is, these are stars coming off of here. But if you look, we've got different networks. So this is a 100 network, a 101, a 102. This is all the 10 network. So our physical and our logical topology can be different, and almost always are different. So some common physical WAN topologies. Point-to-point, that one's pretty self-explanatory, folks. Hub and spoke or star, this is hub and spoke. And then the satanic one, which I call the full mesh topology, where you can end up, with this pentagram. And the reason you would go from this to this is obviously redundancy. This hub and spoke is very nice, but if you go to a full mesh, you can lose multiple links and still have connectivity among all of your different sites. Problem with the full mesh is it's more expensive. You also sometimes get partial meshes, those types of things. So point-to-point, logical point-to-point, kind of blow through that. Here's our most common physical topologies: a star, where we put a switch in the middle of this, and it goes out to each one. An extended star, we have two switches connected by a trunk link. Okay. Bus topologies, they're not that common anymore. They used to be very common, but they're not anymore. The big problem with the bus topology was one, they were very tough to troubleshoot, and two, if somebody happened to break the link, it would take down both sides. So part of the troubleshooting was walking around with a terminator trying to figure out where the actual problem was. And then rings, where you've actually got the devices connected to a ring. Rings do not have to be terminated. FDDI, or fiber distributed data interface, and token ring networks are examples. Token ring and token passing was actually a better method of access method than Ethernet. The problem is it was controlled by IBM, and they would not allow the technology to be shared easily. So, big problem there. Real quick, half duplex, full duplex. Half duplex, you can only send or receive, but not at the same time. This is what I call the BBC or Science Channel Mount Everest method. Base camp to camp 2, over. You know, they always say over because you can't send and receive on a pair of walkie-talkies at the same time. Then the other side can send while I'm receiving. Full duplex allows you to both send and receive. In other words, your transmit pair is connected to the receive pair on the opposite end. And the beauty of that is in full duplex communication, you can be sending and receiving at the same time. And in addition, once you get into a full duplex environment with switches, you should not have any collisions. So this contention-based method of CSMA-CA, okay, should not, even though we're using CSMA-CA, we don't have to really worry about collisions in a modern network. In controlled access, there will never be a collision anyway because you've got either the token or you don't have the token. And if you have the token, you can actually send. I'm sitting here talking to you, and I clicked on Gerald. You had yourself muted. I unmuted you. Sorry. Any questions about why controlled access would be better than contention-based? Why do you think contention-based is not as good as controlled?
With controlled, you aren't going to have to worry about collisions.
Exactly. You don't even need a method for dealing with collisions. Mm-hmm. Whereas with contention-based, you've got to have a method to retransmit because there will be collisions. But what they did is they cheated.
Why did you say that the token ring is better than Ethernet when the Ethernet you're physically connected to intermediary devices on your own line, so you never going to have to worry about it?
Well, you are now. In the beginning, though, we had these true buses. So
okay.
back when we had 10 megabit Ethernet and you had 4, 10, and 16 megabit token ring, token ring was actually a better method because you had no collision. So you got your full throughput close to it anyway on token ring. Okay. The problem with token ring, and the reason it didn't take off, is because the token ring card owned by IBM would cost you $185, and you could buy an Ethernet card for $50. So now Ethernet cards are a dime a dozen.
Back in the prehistoric ages.
Correct. Yeah. In the prehistoric age, I've actually worked on token ring, and it is a pain. It is not something that's fun to work with. But again, at that time, the right moves were, if they had been made, there was possibility that token ring as a actual method, token passing and token ring was better than Ethernet. What Ethernet did, though, is they said, hey, let's just keep making it faster and faster. If we have retransmit, that's okay. We're going to be going so much faster, it won't matter. And then they said, we'll do even one better. We're going to put a switch in here, okay? So instead of a hub, we'll put a switch in, and we don't have to worry about any collisions whatsoever. So they cheated a little bit, but it worked, and it's a better method now. So, I mean, think about it. When's the last time you bought an Ethernet NIC?
I can't remember the last time I bought a computer.
Yeah, I mean, really, every computer has a NIC built in. All of them are gigabit NICs. You know, we don't even really think about it. We're like, I order a computer and I know it's going to have a NIC on it, at least one. Now, when I order servers, I actually do look and see how many 10 gig versus 1 gig versus, you know, NICs. But for the most part, NICs are a commodity now. So it's kind of a different world than what we grew up in. Because I can remember actually buying NICs and paying, you know, $75 for an Ethernet NIC. Back in my day, man, I feel old. CSMA CA is used by wireless, and it's just like CSMA, except for CA, it actually sends out a signal to say it is going to send before it sends. And let's see, here's some frame fields, looking at frame start, addressing, type, control. You see this, okay, and then I want to show you, you got an activity on it. So let's see, when I see something here and I see an activity on it, that's just kind of a little clue for me. Layer 2 addresses, this is interesting. This is something you do need to know. Notice how the layer 2 address source changes, source and destination changes at every single hop. So the layer 2 information is rewritten at each hop along the path by routers. Layer 3 is not rewritten by default, although it can be. We do know that it's possible to do that. So
now, why did they? When I was first learning this, they were saying that the frame gets stripped away, and you're just passing packets as you're going to other networks.
Okay, what happens?
But in this, they're talking about the frame being stripped away and then re-encapsulated in another frame.
Right.
Isn't that just? Go ahead.
No, go ahead. Go ahead.
I'm just thinking that you're stripping the frame away, and now you're just passing the packet, which was the data piece in the frame, in the original frame. Right.
Well, they're only showing up the layer 2 here because this is the layer 2 chapter. But what's actually happening is, of course, there is an ARP request that goes out here, and ARP replies, R1 replies with its MAC address as the MAC address for the destination server, which is the destination IP. So it's going to come in here at layer 2. The R1 is going to bring it in and say, hey, that's my MAC address. So take off the header, run the CRC, make sure everything's good. It's then going to look at the destination IP, find out what network that is, and then use a route table lookup to forward that.
Yeah, I got all that. It's just the terminology that they're using, talking about re-encapsulating at the router at R1. It's re-encapsulating the data in a frame and forwarding the frame. Right. When isn't the router actually passing a packet?
No, it's passing a frame. It's putting it into the correct layer 2 format for this link. So if this is Ethernet, then it's going to put a destination MAC address and a source MAC address. If it's HDLC, it's going to use, really for HDLC, it's point to point. So there's really no need for even a layer 2 source and destination, because if it goes out this side, it's got to go to this side.
Right.
If it's using frame relay, it's going to put the information needed for frame relay for, you know, source DLC and destination DLC. So it does actually rewrite the frame at each when it exits the router.
So there actually is a frame then?
Yes. Oh, yes.
Okay.
It's
because I
was
always taught packet switching and not frame switching.
And I think the reason is because when you think about packet switching, what it's doing is it makes its routing decision based upon the packet.
Right.
Based upon this information, the layer 3 IP packet. But it still has to re-encapsulate it down to layer 2 to get it back across the media.
Okay. That makes sense now.
Okay. Well, good. Glad it makes sense. So, yeah, it definitely has to take it apart, look at layer 3, and then put it back together and put it back on the correct type media and send it across. All right. And that, folks, is chapter 4. Are there any questions? Our next chapter is a whole chapter on Ethernet, which will be fun.
You don't have any smart home devices. To get started, go to the